My name is Aylin Ahadi, and I'm from Lund University, from Sweden. But as I would like to mention, I'm actually born in Bulgaria, so it's really a pleasure for me to be here at this conference. And the topic of my talk is about modeling. So I will have a slightly different approach from the previous talk, from previous speakers. And this work is a joint work between me and my colleague Solveig Melin at Lund University. Well, the previous speakers brought us from the micro to the nanoscale, and on my talk I will stay at the nanoscale and try to see how the mechanical properties differ from those that we are actually used to see at the macro scale. So what we have investigated is the strain rate effects from intensile nano-sized single crystal copper beams. So we have actually loaded nanobeams, regular beams at nanoscale intensile, and studied the strain rate effects and plasticity development. So the material we studied, as I said, is copper and we have studied two different crystallographic orientation, because at nanoscale the mechanical properties are actually dependent on the crystallographic orientation. Except from the orientation, we have also studied the size effects. So the beams that we will see here shortly, we have different sizes actually. We have studied 3 different sizes. And the reason for that is because it's well known that the mechanical properties at nanoscale are actually size dependent. We observe size dependency both, for example, in the Young modulus and the yield stress and so on. All right. So the simulation that we have done are done using the molecular dynamic simulations, and we have used the classical molecular dynamic code called LAMPS. And the modeling is done by a potential function which describes the interaction between the atoms. In this case, we have used the EAM potential function comprising of 2 terms, where this first term here is a pairwise potential function, and then we have an additional term here comprising the embedded energy and the electron charge density. If you're familiar with the molecular dynamic, in some way, then you could recognize that this first term here is what is present in the Lennard-Jones potential function, and then here we have an additional term. Well, to study the mechanical properties, we need some measure for the stresses. And this is the measure that we have used in our computations. The stress here consists of 2 terms, where the first one here comes actually from this potential energy function, and the second one, you could recognize that those here are the velocities. So this term here originates from the kinetic energy terms, and those velocities are the individual velocities, the atoms, individual velocity, atoms' velocities. Well, this is some details about the simulations. I will skip that. Okay, so the copper material that we study has a unit cell, and the dimension of each unit cell is 3.6 angstroms. And this is the length of each beam, so 300 unit cells. And we have 3 different cross-section sizes and 2 different loading directions and some different strain rates, velocities, end velocities. Okay, so the result that I will present here will be a parameter called the central symmetry parameter. So this parameter is actually a definition of some kind. That it tells us something about how distort the crystal is. So for small values, if we have a perfect lattice, then this parameter will be actually 0 or less than 3 if we are close to the perfect lattice. And then there are numbers here. We can, for example, see that for a surface atom, it will have something between 9 and 25. And edge and corners are especially interesting. So there we have numbers above 21. And this parameter is, okay, how is this calculated? We take one atom here, and we take the nearest 12 atoms in that case for FCC, and then we end up with a number which we calculate in that manner here. This is just to illustrate. We start with a beam. In the beginning, this beam is, it's not loaded, and you can see if we plot this central symmetry parameter with all the red atoms, we have the values between 21, below 21, and the blue edge atoms we have higher, and then here we load the beam, and as we load, we can see new edge atoms develop here. So this is just to see some, that you have some idea what we will see in a moment here. All right, so we have studied 3 different sizes. You can see here 6, 12, and 18 of the cross-section, and different end velocities. And what we have recorded is when the plasticity initiates and when we have a fracture of the beam. So if we look at those 3 curves here, we see that this is when the plasticity initiates, and there is almost no difference between the 3 sizes here. Although we can see that depending on the end velocity that we load it with, we have actually a decrease in initiation. The 2 diagrams, the left and the right one here, they refer to the 2 different orientations that we have studied. We can also see that there is actually a quite remarkable difference between the 2 crystal orientations. The curves that we see here, they are when we observe the first fracture. And the reason I call it the first fracture, I will explain that later. I think I skipped that one. Well, what we see here is the strain curves of those 3 sizes of the beams. And I will just tell you not that much details, but something that is quite interesting. If we look at the initial parts here of all the curves, what we have at the those initial parts here is that the beams are elastic. And what we clearly observe, especially for that orientation here, that we have a nonlinear elasticity all the way. This is not something that we do not observe on the global scale. If we look at that direction, this part here is actually also nonlinear, but it's a little bit more hard to see from those figures. So the nonlinear elasticity is what we observed. What we can also see maybe that the slopes here are not the same. This indicates that the Young modulus is actually size dependent. So if we try to calculate the Young modulus for those 3 sizes, we'll have different values. And if we look at the top points here, those top points here, it's when the behavior transits from elastic to plastic. So what we actually can calculate here is the yield stress for those beams. And if we look at the yield stress, we can clearly see, well, first we can see that we have different yield stresses depending on the orientation. The yield stress also differs with the end velocity, and there is also a difference or size dependence of the yield stress here. And then some snapshots from the simulations, 2 different directions here. 100, 110, and we start loading the beam, and then after a while we can see that here we have the first fracture of the beam. But what is interesting that if we look here, later on, it actually, we can see the second fracture. We can also see it from this direction here. And this is something that we never observed on the macro scale, because once we have a fracture, then the beam should, well, we have no load, right? But at the nanoscale, we can actually see that. And this is what we can also see if we look at the larger sizes. This is 12 unit cells and 18 unit cells here. And for 110, sorry, we can see that we also have fractured two places. This slide here shows the cross section, so it's in the middle of the beam. And what is interesting to compare here is the two directions. And if you, here we start at the start of the simulation, and here at some axial strain. And what you see that the cross sections here, they're completely different. So depending on in what direction we load the copper beam, we obtain a completely different cross section. And I'm not sure if it's seen on that cross section here, but what you can see here for 100, those sizes here are almost of the same length. But for 110 direction, this side here is much longer than that one here. And if we actually calculate the Poisson's ratio for those different directions, we will turn up with different values for the Poisson ratio between this and this direction, but also we'll have a different Poisson ratio in that direction for the same orientation. And then those will be my final remarks. I just left it for you. This is something I already mentioned. So thank you very much.